science like there's no tomorrow.
Hello, welcome everyone to lecture number 11 of the financial engineering course. Today we will have two important subjects to cover. The first subject is the Libor market model and its extensions with, for example, stochastic volatility. And the second subject is the convexity correction, convexity adjustment. Here we will learn what is the convexity correction and how to model it using some model choices that are common in practice. Let's take a look at the content of today's lecture. I have prepared today two blocks. So the lecture is divided in two pieces. And here it is. So we start with a little bit of history. What is the motivation for the Libor market model? What were the problems before actually Libor market model was developed? And what are the applications of the framework? In point number two, I will discuss the model specifications. So we'll go into details on the model dynamics and what are the possible choices for different specifications for the Libor market model. Actually, what are the dynamics for the Libors? So the whole Libor market model is defined in terms of dynamics of different Libor processes. The whole idea of the Libor market model is about bringing all the individual measures of all the individual Libor rates into one consistent measure, and that allows us to evaluate to price a derivative. Maybe you remember already in this course, I have told you, presented that if we have an expectation, it's not maybe nice expectation, if we have an expectation under measure, some measure, this expectation involves a payoff, and this payoff would depend on process, let's say x1, x2, and so on. All those processes which are undefined under this expectation, they need to be under this measure. This means that every process that has Brownian motion, so for example, this will be Brownian motion 1, has to be under measure A. And the same will be for process 2. So here we have Brownian motion 2 of A. So the Libor market model is about bringing individual Libor dynamics processes under one consistent measure. And you will see this is not really trivial extension of the Libor rate itself. So this involves advanced measure time techniques, but using the knowledge that you already have gained in this course, in particular from lecture number 2, that will be easy to follow. Then we have, of course, we start with the specification of the Libor market model on the P measure, and then we move to forward measures, and then we start with the derivation of the Libor market model. Here we have two possibilities, so of course, maybe more possibilities, but we will discuss two popular choices: Lognormal Libor market model and extension with stochastic volatility. I will show you that if you take the Libor market model, the dynamics for each individual Libor, and you simply assume Heston dynamics with correlation between the variance and the Libor rate, that would lead you to some significant issues. And those issues would be related to measure changes. In short, the dynamics for the variance process will become extremely difficult to handle. For that reason, we will go into the, here in this point, we will discuss the extension of the Libor market model with stochastic volatility and displaced diffusion. In that way, we'll be able to calibrate the model to implied volatility, smile and skew, while having kind of attractive features of the model that this difficult measure change will not destroy the dynamics of the variance process. There are two, also here I will discuss two popular choices regarding the measure choices. So whether we evaluate trades under the terminal on the spot measure. So it's a big difference between these two approaches. We will spend some time to also discuss what are the first, how to derive the spot measure on the Libor market model and how to price derivatives under these two measures. And this is the stochastic volatility. I will also mention here the concept of Libor freezing and how this freezing can lead you to some significant issues once you deal with Libor market model, how you can destroy your model dynamics if you abuse this popular technique. In the last part of this lecture, here we will concentrate on the convexity corrections. What are the convexity corrections? When you can expect to see one, and how to model them, how to evaluate a derivative that involves convexity adjustments. And I will finish this lecture with summary and some 3 assignments that you have to do this week. I hope you enjoy it, and this is, I think, nice two blocks before we go to the final step of this course where we talk about XVA and VAR. I think it's also important to understand how Libor market model, how convexity corrections can be used, and how this knowledge definitely will pay off in your future career. Good luck. In lecture number 3, we have discussed 3 categories of interest rate models: equilibrium models, short rate models, and also market models. In case of market models, I have compared those processes, those models, to a tank. This means a very powerful machine to solve very serious problems. And this is also advantage and disadvantage of this framework. So indeed, if we compare Libor market model or market models to a tank, we can see that this is extremely powerful machine. It can be used in a variety of problems. However, from the practical perspective, it is often very problematic, especially if you would like to go for shopping, let's say. Driving with a tank, it's a really troublesome. On the other hand, the maintenance-wise, so maintenance perspective, it's also very expensive. In those similarities, I have used to compare market models to a tank, which is also clumsy and, however, extremely powerful. The whole purpose of the Libor market model or market models is to use those models to pricing of exotic derivatives. In this sequence of lectures, we have discussed many different types of payoffs, and I have shown you that in most of the cases we have considered short rate model, in particular the whole white model, was good enough to perform some pricing. Of course, if we could extend those models to make more smile dynamics to be more efficient. However, if we talk about callable models, callable payoffs, for those we haven't actually used in short rate model, we haven't discussed the exotics. Libor market model is actually designed to handle callable and very complicated advanced payoff structures. So let's go first to the history of the framework. So the framework was already developed many years ago. It is initiated by Brace, Gontarek, and Musiela, who developed this framework of connecting different Libor rates into one coherent framework. Already in this sequence, we have discussed the Libor dynamics, and Libor is always a martingale under its own measure. And this is basically what was very beneficial we have seen in terms of pricing. However, the problem is that what if you would have payoff that would depend on multiple Libor rates that are defined in different measures? What is the machinery such that you can combine all those Libor rates into one measure? As you remember, if we have generic pricing equation and we have some measure here A, I always mention that if we have some payoff here, let's maybe without dots, if we have some payoff, we have to do discounting, let's call it with also A. And if payoff here, this payoff V, depends on some processes X at the maturity time T, all those processes have to be defined under this measure A. And this is the key point, because if we have a payoff that would depend on multiple Libors, those Libor rates, they have to be defined under one measure. And this is exactly the task of the market models or Libor market model in particular, that brings different Libors with a different dynamics into one framework that is allowing us to evaluate those expectations under one measure. In this lecture, we are going to discuss details about these measures and what is the preferred choices for choosing on this, let's say, unified measure for pricing purposes. This framework also allows in many occasions for some closed form solutions. However, because of the complexity and the multidimensionality, you should not expect that you can price exotic derivatives in using closed form expressions. And the whole machinery, this is very important also to highlight, it relies on the measure change techniques and the so-called forward measure. So we are already familiar with that. Forward measure associated with zero coupon bonds. This is also related to the Libor dynamics that we have also discussed further already in this course. And what is also important is that in lecture number 3, we have discussed this generic HJM framework, the Hitler-Morton framework. This is super generic framework for defining interest rate models. And for that framework, we have specified number of conditions, especially drift conditions, such that drift related to volatility conditions, such that the model is well defined and is arbitrage free. And actually, the labor market model I will show you also in this lecture today, it also belongs to this generic class of Hitler-Morton, the HJM framework. So this also ensures that this model is arbitrage free. Another point, complex fixed income products, so such as various kinds of path-dependent swaptions, usually involve cash flows at different points in time. So those exotic derivatives I already mentioned, and in that framework where we cannot use simple LIBOR, we don't have a European type of payoff, especially if a payoff that depends on single LIBOR, but depends on multiple LIBORs. For example, a product of LIBORs, or let's say it's some kind of compounding effect, or we are observing path dependence, then we cannot use simple European type of evaluation. We need to have much more advanced models. As the valuation of these products cannot be decomposed into sequence of independent payments, so this is the case, for example, as we have in a swap rate. In a swap rate, we have a sequence of payments that take place in some time. So that's always beneficial. If you have a sum of payments, you can decompose them and price them individually. And this is what we have done for the swap rate, where each individual swap payment was evaluated under its own measure. So that in that case, we don't need LIBOR market model. We can simply rely on individual expectations. So in that case, it is a challenging task to develop a model which is mathematically consistent and agrees with well-established market formulas, like with variance of Black-Scholes for pricing of interest rate derivative. So here what I mean is that in previous lectures, we have defined the Libor dynamics. So it's Libor dynamics, let's say ith Libor, so the payment is at time ti of t. We have already discussed that we have this sigma I L t dw. Here we have this forward measure. So you see that if we have a payment that only depends it only depends on the payment at time ti, we have a payoff, European type of payoff of a LIBOR. We can simply, actually in this case, if we talk about couplets or florlets, we see that this is a log-normal distribution. We can simply apply Black-Scholes equation. So it's called Black's 76 to evaluate option on this LIBOR. So maximum of Li capital time T I minus K0. We have expectation under this Ti measure with a zero coupon bond in front, Ti. So you see this can be evaluated with a Black-Scholes equation. It's called BS, Black-Scholes model or a Black 76. In this case, we can simply do it. So you see each individual LIBOR allows us to evaluate pricing of European options with the Black-Scholes model. But if we have a payoff that would depend on multiple LIBORs, and all of those LIBORs are martingales under their own measures, there may not be martingales under one common measure, let's say Ti. Then we need more advanced model, and then this is exactly the purpose of this LIBOR market model or the market models in general. When defining new model, like model of a LIBOR market model, which is also called often Brace-Gontarek-Mushel model or simply BGM model, the greatest advantage of this framework when defining this model took place was that developers or the creators of this LIBOR market model, first they were approaching this problem from a very practical perspective. So the idea was to say, okay, what is happening currently in the market and how we can create a model that will not only be coherent and consistent internally and will not allow for arbitrage, and at the same time will be consistent with market practices. And this is exactly why this model was addressed widely, because essentially it did not change how market evaluated swaptions, LIBOR options on LIBOR rates, But it was defining the framework which didn't disturb the current practice for pricing. On the other hand, was defining the relation between all those building blocks present in the market and allowed for pricing more exotic derivatives. So you can imagine that the blocks of existing blocks in the market were already created, and BGM, the Brace Gontard Musiela, they've connected all the dots, all the pieces that they were currently used in the market, and based on that, they developed new framework, which essentially was collapsing to the practices in the market, and at the same time was allowing people to price exotic derivatives. This is why this model was so popular. It is still very popular, and this is the strength of this model. If you would just define a new model, and I think in the past, many people defined new type of models which required market changes, how market operates, would require some kind of calibration or changing the procedures. This is typically considered to be less attractive. If you have a model which complies with the market practices and adds something extra to the framework, that's always considered to be advantageous, and very likely your model will be then accepted as the market practice. And this was the case for Libor market model. It was considered and is considered market practice for pricing of exotic derivatives that depend on multiple Libors and often callable structures and so on. Maybe one more thing to mention regarding Libor market model is that the simulation of the processes involved in this model, it is in majority, I would say 100% even, using Monte Carlo. So from PDE perspective, from let's say discretization of the partial differential equations for Libor market model, it is very, very limited. I have seen only few attempts to do that. The problem, of course, here is the dimensionality. As you will see later in this lecture, once we are trying to develop a model or glue multiple Libors under different measures together into one framework where we can have Libors under one measure that we can use those for pricing of derivatives, dimensionality becomes a really significant issue. And from a practical perspective, Monte Carlo is often the preferred choice. So the concept of developing a new model is that it should provide arbitrage-free dynamics for all the Libor rates and has to facilitate the pricing of couplets and floor rates in a similar fashion as market conventional Black-Scholes formula. And this was related to what I just mentioned to this equation. So in the market in the past, or actually even now, if you have an option on a couplet, so if an option on the Libor rate, then assuming log normality for the Libor dynamics, of course, these days will be also additional shift parameter, you should be able to price with the Black-Scholes model. The concept why the Black-Scholes model is good enough, I don't want to dive this time into the subject. The problem of choices regarding different models, I will discuss in a follow-up course. We will concentrate on the market practices depending on different markets, different dynamics, and also choices that people have to do when decide to which model is more suitable for derivative pricing. But what is important here is that the market convention in the case of Libors, couplets, floor rates, was using Black-Scholes formula. That was the market, or that is a market convention. So of course, the new framework has to collapse to this basic fundamental block. On the other hand, so let's just refresh a little bit. I think we already have seen this before multiple times in this course. The definition of the Libor rate, which is so we have 3 dates. So Libor rate has 3 dates. We have this running time. So because this is a stochastic process, it's a value, it runs in time. And then we have 2 important dates that determine what type of process we have here. So those you never change. This is basically characteristics of the Libor rate we are interested to observe and use for pricing. The first date is called reset date. So date at which the rate will be fixed. And then we also have a second date telling us what is the pay date of this rate. So when this amount accrued over this period of time will be paid. So those are very important dates. And of course, depending on the distance between ti minus 1 and ti, then this dynamics of L will be different. There could be less or more volatility. This is also something we have discussed in the case of multi-curves. when a distance, this accruing period, also defines a curve. And then we have also in market practice, we have curves, multiple curves, multi-curve framework, depending on the standard structure of LIBORs. And here's the definition. Previously, I have derived those, and we went through those steps, how this is related to zero coupon bonds. Of course, the key element, the key point is that this LIBOR would be martingale under this T forward measure, because you see this is numeric, this is tradable asset, so this has to be martingale under this measure. And this is a relation to HJM framework and also the so-called forward zero coupon bond. So if we define forward zero coupon bond as kind of a refinancing strategy between time T1 and time T2, and we define simple compounding rates, then we can also, in this way, we can arrive at the LIBOR rate just in the same way as we have done it before in this course. So just to summarize here, we have those two important dates. We have this reset date. It's also often called fixing date. And then what is also important here is that these reset dates, they could also be slightly changed. So if you're becoming a financial engineer in the future, I hope that you will see that in practice, if we deal with LIBOR rates and also interest rate structured products, then if we have those reset dates that you can that we just defined, in practice we have some more dates in the payment schedule or in a general schedule of the rate. So first one is that if we look at this reset, we have something which is called also reset delay. It can go either way, which is additional date that we have to take into account. So this means that the fixing of the rate could be different, slightly different. There could be some delay with regards to the date that this rate is observed and actually when it resets. And the second part, we also have the second date. So we have a pay delay. This means that if we have a time t here, there could be also the rate is known at this point. Of course, this is our pay date. However, the payment, it will take few days after. But however, from the modeling perspective, we often just make them equal. This is much handier if we have, especially if those two, say the tau that we have used here, it's very small, and this distance between ti and ti plus tau, it's small, then this effect of this approximation is very small. Later in this course, I'll be talking about this kind of phenomena where we have a pay date at one date. However, the underlying measure corresponds to a different date. So there is a mismatch between the payment of the product and the discounting. Then we have to deal with the so-called convexity adjustment. So whenever we have a payment taking place at one day, however, with discount from different date, then this means there is a misalignment between the underlying asset and discounting. And then this is not necessarily anymore a martingale. There are some problems with those kind of specifications. And then we have to do some kind of correction to account for this impact, because there is some period which is not included in this expectation. Later, I will show you how this can be handled and what are the tricks and tips if you're dealing with a convexity correction. Maybe the most important takeaway is that if this distance between ti and ti plus tau it's small, then typically this impact and this effect is extremely small, because this distance here, it's a function also of the volatility and the time. So the error is a function of the distance and volatility. We start with a specification of multi-dimensional LIBOR market model. Of course, it's always the most challenging part is to start with a model under measure P and then find dynamics of this model under the risk neutral or the forward measure. So what we do, we specify number of LIBOR rates we are interested in. So of course, this will depend on a particular payoff we have to deal with. So if your payoff would depend on 10 LIBORs, then you need to have defined a 10-dimensional LIBOR market model. If it's only one, of course, this is trivial case, because then we are collapsing to the dynamics of a single variable. So here, let's keep it generic. So we have a 1 until m. And so we have for every Libor I, so we have those Libor I's, it's Libor T, Ti minus 1 Ti. So you see we have for every different payment date. So if you build a time grid with a T1, with T2, with T3, and so on. So the first Libor rate, so T0, would correspond over this period. Of course, if we are, let's assume that we are here. So the first Libor would correspond to the rate over this period. So this will be stochastic until this moment. The second rate, so this Libor 2, would be Libor over this period. That Libor would be stochastic until this moment. Then if you look at the Libor number 3, so we have this one, this period, then the stochasticity here, will be stochastic until this moment. So you see we are kind of having a system of Libor rates, but if we see that if we go in time, in this case actually the dimensionality of the system would decrease. Because if we are, for example, are here, those Libors which are determined before, they are not running anymore in time because they were fixed. So the first one was fixed at time t0, the second was fixed or reset at time t1, and so on. So you see this is a very interesting structure of stochastic differential equations because we have processes, we start at this point with m stochastic processes, but as we go in time, some of those processes, they will be going away from the system of stochastic differential equations that we have to simulate. So we start with m, after the first period we have m minus 1, after second period we have m minus 2, and at the end we end up only with one Libor left. Of course, after the reset of the last one, there is no more Libor left. So this is very interesting structure of a process. Of course, we still have to find the dynamics under the measure of interest. And of course, as you can imagine, all those rates, especially now in this period, you see they are observed in the market. So of course, all those rates are correlated. So this period is correlation here. We also have correlation there, and so on. So there is a correlation structure between all those Libors. And of course, you see the correlation matrix also changes in time. It becomes smaller and smaller because some of those Libor rates already known. So there is no more point of correlating them with the remaining assets, the remaining underlying processes. So it's a very interesting structure of those Libors. And the correlation, this is the correlation between all the Libors. It's also possible to define it to be time dependent. I'm not going to show you how this definition should be done. Typically, it's done via some parametrization. So the relation between Libors, so if you have two Libors, the first Libor over this period and the second Libor over this period, you can define parametrization for this rho such that if Libors are close by each other, so Libor 1 and Libor 2, then the correlation is the highest. And for example, if you have correlation between the first one and the last one, the correlation is the lowest. So you can define some kind of parametric forms of the correlation structures of the Libors, and that you can also calibrate by using products like CAPS. So there's let's say, established literature, you can look it up, how this correlation calibration can be performed and what type of correlation structure you can define. Of course, it is important that if you define some kind of parametrization for correlations, you have to make sure that your matrix of correlations is positive definite. And this is exactly what the parametrizations are about, because often, actually always, if you talk about parametrizations of correlations, the parametrizations are created in a way that by default are always making sure the correlation is positive definite, the matrix is positive definite, and of course that's the necessary. Otherwise, it's a bit problematic issue if you have a 20-dimensional matrix and some of the correlations cause your matrix not to be positive definite, then of course it's a big issue how to fix it. It's a whole, let's say, research done. What are the possible algorithms that you can fix such a matrix? But if you define parametric correlations, that's good enough because then you don't have many parameters. You have maybe 3 or 4 parameters, and then you can fit already to the correlation structure or some products in the market, while you're keeping the number of parameters very low, and at the same time, you're making sure that your matrix is positive definite. What we do next, we define the forward measures, since we have seen it already many times in this course. The forward measure, TI forward measure, will be associated with the zero coupon bond PTTI. So this corresponds to this number here. And so, of course, now what we have to do, we have to define some martingales and processes. We have to move from the real world measure P into Q measure. And of course, here is a little bit of summary. This is also what we have seen before about the result from Harrison and Krebs about the martingales and measure changes also to some extent. So if we have tradable assets, we have those two zero coupon bonds. We know that this is a numeric, this is a tradable asset. So of course, this quantity has to be martingale in the TI measure. This means this has to hold. So this is equality here. And of course, if we just apply the definition of a Libor, so if you multiply with here, if we this expression, this ratio of these two zero coupon bonds, we can relate to definition of a Libor rate. So obviously there is no more, let's say, it's just a simple equation. There is no transformation essentially of this, because Libor in essence is just a ratio of these two zero coupon bonds with a constant multipliers, and we add something small, some one somewhere, then this means that this is also a martingale. So this is something we already have discussed multiple times. And then, of course, as a consequence, we can write this, that Libor rate, TI Libor rate under TI forward measure is simply written by it is a martingale, so it is equal to the Libor at time t. And of course, those two parameters, whenever you change measure, they never change, because those are, let's say, characteristics of our process. So if you say I have stock 1 or stock 2, now we indicate Libor processes by two indices corresponding to the tenor structure in our model. And of course, this result can be explained by simple analogy, since 1 over 0 coupon bond PTI minus 1 TI is a martingale under TI measure. So of course, this same has to hold for the Libor rate. So this is very simple analogy that we can use to also to prove this this equation. And of course, so if we know that the Libor L T and this is T and the TI minus 1 is a martingale, then of course we have to we know how this stochastic differential equation will look like. We know that under the ith measure, then we have a martingale. So we have a process without a drift. So we can define some function sigma I bar. These are the generic function, and then we have a Brownian motion. But of course, keep in mind that we have a first Libor L I. We have a sigma I dw, and here I. This is also it. We have also d will be, let's say, j. We have a sigma j dw j, and this is also j measured. So we see that for Brownian motion, we have two indices. We have index telling us to which Brownian motion, to which Libor it corresponds to. So we see this is Brownian motion I corresponding to I Libor. However, the second part, this can change because this is a corresponding measure. Later, I will show you that if we start changing measure for Libors, this index here, this will change. But of course, here we are having m different stochastic differential equations because we have m Libors, so we have m Libors. So you see, it's a huge system of Lognormal, or actually whatever sigma you choose processes. And of course, each of them, it is defined under different measure. So of course, in this way, they're rather useless, because if we have an expectation under measure, let's say, let's do it k, then we cannot just use this, and we have some payoff, let's say, function f of those Libor 1, Libor 2, and so on. If you would like to calculate this expectation, we cannot simply take the solution for this Libor and plug it into this expectation, and this one here, and so on. No, we cannot do that, because those processes, those LIs, they have to be defined not at measure 1 or measure I or measure j. All of them, they have to be defined under one measure k. This is also something we have seen previously in this course, that there is always has to be consistency between expectation, measure in the expectation, and also the measure or the Brownian motions that are used to evaluate some expression. So this is the key point of the Libor market model, or BGM model, where the individual assets as we see in the market. They basically corresponding to some market practice of pricing using Black-Scholes model. They are put together to actually how to use them together such that we can find one consistent measure that we can evaluate our derivative. And this is basically the whole idea of the Libor market model. We start with multiple stochastic differential equations and we bring them together all into one consistent forward measure. And then we can, by changing different measures, we always have this consistency between all those processes together. So you see, we essentially now you can see they're kind of independent processes, although maybe their emotions are correlated. But a Libor market model brings all those processes into under one consistent measure. So each Libor under its own measure is a martingale, and if you would like to bring one Libor into the different measure, of course, that will have consequence that the drift will be introduced in the dynamics of that corresponding Libor rate. So this is how it would look like. So if we have a Libor with a payment, so this Libor is L, we have a Ti minus 1 Ti. We know it's a martingale under the Ti forward measure. And if you would like to change the dynamics, the measure from I to J, this means that you will have additional drift factor. And the key element of the Libor market model is to find out what is exactly the transition of the drift, how this drift behaves if we change Libors and we change the corresponding measures. So we have a one Libor rate, but we change measure, that would have impact on this corresponding drift term. And this drift term, actually, it will happen that depending on the measure J, it can be quite complicated. It will be a running summation over all the Libor terms. And of course, this is also important, depending what measure we will choose. Later in this lecture, I will explain you two common possibilities, whether we choose to price derivatives under the so-called terminal measure, so the last Libor in our simulation model, or we choose so-called spot measure, which corresponds to the closest tenor of in our simulation. But this will be discussed later. So here we have this generic case where we have the sigma I bar, and of course, if we go to the log-normal case, so this is log-normal Libor market model, and then we have a specification when we have a sigma bar is equal to sigma IT. So this is some time-dependent function, and here we have a Libor IT. So if we just substitute this term into here, then we end up with a log-normal Libor market model or log-normal dynamics for each corresponding Libor rate. And this was also illustrated here. So here we switch back, so we don't have any more J. So this is not anymore J measure, but we have I measure. So we are going back to be that the process for Li is a martingale. This means that we can just substitute, and you see if we divide both sides by Li, this is the dynamics. And the most important, of course, here is that if we choose the sigma bar I, then we can choose different processes, different dynamics for the Libor market model. In this lecture, we will discuss a few of those configurations. Especially important one will be the one involving stochastic volatility. And then what is very important there, the relation of stochastic volatility and the correlation. Because what is very interesting is that if we have this process here for volatility that will be stochastic and also correlated to all the Libor rates, then the dynamics of the volatility, stochastic volatility, becomes extremely complicated. And that will be presented also in this lecture. So to overcome those issues, we will have to do some choices such that still our model allows to calibrate to implied volatility, smile or skew. And at the same time, we preserve those qualities here like martingalities under the corresponding measures. Another thing I would like to discuss in this lecture is the relation to the HJM, so Libor market model, Brace-Gontarek-Musialis model, and the relation to the Hijaro-Morton model. And remember, maybe in lecture number 3, by specification of the volatility for the instantaneous forward rate, we could choose between different models. In this course, in particular, we have discussed full Lee model, full White model, and now is the time where we talk about the Libor market model. Here you can see that we can also do that with the Libor market model by specifying this kind of form for eta, so this full white volatility for the instantaneous forward rate. If we choose of this form, then we will go back to our this will define the Libor dynamics under its corresponding measure. So this is nice relation. Of course, those derivations may be a little bit of algebraic. You have to do some derivations, but this is just to show you that there is still a relation between HJM and LMM. And of course, if we think of this instantaneous forward rate, which we had here, so here we had this forward rate TT, and now we have a Libor rate, which was LT TI minus 1 TI. Of course, those two things are very much related. So this is, let's say, this is a special case when those two times will be approaching each other, and we have a running index. So, and this also shows you what is the volatility function, such that we see directly the relation between volatilities from HJM and Libor market model. And here is again the dynamics of the Libor market model with this generic case sigma bar without specification with this Lognormal. What we are going to do in the next step, we are going to change our measure. So we will switch from measure I to measure J, that will be generic case. And then we will find out what is this, actually this drift term here, depending on a measure transformation. So let's do that. In lecture number 2, we have discussed the concept of measure changes. So you can see that actually we are getting closer to the end of this course, and we actually strongly rely on knowledge that we have gained in this course in previous lecture. And this is also important to put attention to all those previous lectures, because those tools we will be using heavily, especially in the last 2 lectures, when we'll be talking about simulation of XVA, of exposure simulation, and also of pricing of a VAR and expected shortfall. So here, if we go back to this Radom-Nikodym derivative, which allows us to transform measure between different measures, so we can transfer the process between different measures. So here we have a measure transformation from I to I plus 1, so these are T forward measures. This is this Radom-Nikodym derivative, often denoted by a lambda. And here we have this relation, so this is this derivative. As you remember, we start from the denominator, we have always the quantity at time t, the ti minus 1, actually here we have then divided by value at the initial point. Then we look at the denominator, we have an opposite. So we take the beginning divided by the time t. So this is easy cross terms that you have to relate. And then this relation, if you always follow this strategy that you evaluate first the value at the end, the corresponding measure divided by initial point, and then you do opposite for the other terms. So here in denominator, this gives you this Radom-Nikodym derivative. And from here, we can find the dynamics for lambda. And that dynamics of the lambda will tell us exactly what is the transformation between Brownian motions under different measures. And this is actually the key element here. Of course, right now we are switching only from measure I to measure I minus 1. So this, you see that if we had this Libor time, we had this, we have here T0, we have T1, we have T2, T3. We have this Libor here, we have a second Libor here. So now we are actually showing what are those 2 Libors. Let's go to Libor 1, Libor 2. We only consider now 2 neighboring Libors. So only Libor 2, how it will be expressed under the L1 measure corresponding to this particular pay date. So it's only 2. So it's only the relation of the 2 consecutive Libor rates. Later we have to generalize that to any measure. So for example, you may have a first Libor and under the terminal measure. So this means that you have the relation of this Libor to all the Libors in the future until the terminal point of our simulation grid. Okay, so let's go back here to the measure transformation. We have, first of all, we have to notice that which quantities are constant and what are the stochastic quantities. So of course, this quantity, this zero coupon bond, is deterministic. The same is here. So those are constants. And then we have these 2 zero coupon bonds. So if we take this lambda I minus 1, these are the constant terms. And of course, this term here, we can easily relate to the dynamics, actually not to the definition of the Libor rate. And this definition is actually here. So tau I times LIT, so the Libor rate plus 1, this will be exactly equal to the ratio that we see here between the corresponding, these 2 zero coupon bonds. Okay, so, and this term is constant. And of course, now, next step, if we have this term, we see this is stochastic, because this is everything is constant, constant, constant. What we do next, we define the corresponding dynamics. Of course, dynamics in this case is trivial because we have only the constant terms in front. So if you do dynamics here, all these constants will go outside of D, and then of course this one will be gone because the dynamics of one is just 0. So then we end up here. Dynamics for lambda is equal to the dynamics of Libor rate multiplied with some constant for action term. In the next steps, of course, what we have to do is we have to substitute the definition. So here what we do, we substitute the definition of the Libor rate, so the dynamics of the Libor rate under that corresponding measure. And then what we will do, we end up with those terms. Here is a little bit of, you see, I did a few more steps because what I have done, first I substitute the dynamics of the Libor rate, and then also I have, let's say, extracted this lambda I minus 1. Because this is exactly the essence of a random-Nikodym derivative and a Grzelak theorem that we have to have we need to have dynamics of the following form. We need to have I plus 1 of t, and then we have some, let's call it psi, and then we have a lambda I minus 1 t dwt. And actually what is important is that this always, if you do measure transformation, you have to keep this form. So we have the lambda I minus 1. We need to also have here lambda. And the term which is here will determine, will actually indicate what is the measure transformation between switching from I to I minus 1. So this is a few steps necessary to arrive at this equation. In the book, you will find more details on all those steps. So if we have this, then actually by using Grzelak theorem, we know that the measure transformation between I minus 1 and measure I minus the term which we have here. So this is the Grzelak theorem. We take all this term, minus with minus 1, and then dt. So this term represents this relation, shows us the measure transformation from the ti minus 1 measure to measure I, or opposite. Yeah? So we can also switch from I measure to I minus 1. So the next step would be to substitute. Of course, now we start with the definition of the Libor. We would like to change the measure of I to be in I minus 1 measure. So we just take this term here. We substitute, of course, with this expression. So we just take this part on the other side. And this is the expression what we have. So this here, this dynamics here, shows us the dynamics of the Libor, ith Libor, under the I minus 1 measure. And of course, now we only have this consecutive changes. So it's here, for example, it's 1, it will be 0, or it will be 2, 1. Because now we would like to generalize that to any type of, any measure in the whole grid of Libor rates. So this is what is done here. So this is first, before we go there, to the, let's say, generic case when we transfer between all these different random, let's say, points in the grid. Here we can also move to the other side. So here we moved from I minus 1 measure to measure I. We can also do, of course, I measure to I plus 1. So it goes both ways. So we have, again, this time grid. We have time t0. We have a time here 1. Let's make times t0, t1, t2, and so on, t3. So now if we are we have this Libor and this Libor, we can either this Libor, so this Libor can be represented under, of course, under this measure is a martingale, that we can move either to this direction, or we can move to this direction. So this Libor rate can be represented under the ti minus plus 1 or ti minus 1 measure. And of course, later we'll be talking about particular choices, because at the end we have to decide if we have a derivative that we would like to price. We have to specify what is the best pricing measure for that derivative. And there we distinguish actually two different cases: spot measure and terminal measure. So this is related actually which point on this grid is chosen to be the reference point of pricing of derivatives. And in next block I will discuss these two particular choices for the pricing. And I think that will be it. So here is a little bit of summary about Lognormal distributions and the measure, of course, the measure transformation. Keep in mind, spot and terminal measures, those are keywords if you talk about the Libor market model and measure transformations. The specification of the terminal or the spot measure depends on a choice regarding the numeraire that's decided for the measure, the corresponding pricing measure. So in the terms of a terminal measure, this is very simple because you remember we have this time grid, we have the first library here, we have the second library here, and so on. And if we decide that all those libraries that we have in our library market model should be defined under the last measure, last point here, so this is typically the last coupon that we have in our simulation or our payoff dependent, then all the libraries in between, all of them, they will need to be brought to this measure. So this means that if we have first library here, this library, it's a martingale under its own measure, but because we specify as the pricing measure for our payoff is the terminal measure, so this one, this means that this library will need to have all those drifts. The drift correction should involve all the libraries. So we can see that this is accumulating until this period of time. Then if we have a second library, this library will need to, also this measure will need to be changed to this point, and so on and so on. Only the last library, we can call it, it's some sense lucky, because the last library, it will be martingale under TM measure. But all the other processes, all the library dynamics will need to be adjusted to be corresponding to this measure. In the previous slide, I have shown you how to iterate, how to change measure from a measure time ti, so forward measure, to, for example, ti minus 1, or, for example, ti. So we could go either way. So if we are this library here, we could switch to this measure or this measure. And of course, here, if we iterate, if we continue with the transformation, so we are not only switching from one measure ti to ti minus 1 or ti, sorry, this is plus 1. If we continue this iteration, so changing from ti plus 1 to ti plus 2 and so on, we can actually derive the transition not only by one step, but also by two steps, like it's, for example, down here. So we have a measure, forward measure ti, and we switch to measure ti plus 2. And if we iterate, so if we iterate until the last coupon, that will be corresponding to the TM measure, and then we have this expression. So you see, we have now, instead of one term for drift, actually one element of the summation, now all those libraries will need to be brought to the final terminal measure TM. So this is the transition. So this means all the libraries that we have, they will need to have these adjustments, and depending on which library we are looking at, the number of elements in the sum will be smaller or larger, depending, of course, whether we look at this library. And of course, this library would have the most elements, and of course, the last one will have only 0 elements because it's a martingale under its own measure. But this part actually tells you about the measure transformation for all the libraries in our model. And of course, this is the essence of the library market model. The key is to bring all the libraries with a different dynamics under one consistent measure, and then we can derive our payoff under that measure. So if we change measure of our payoff to be under the terminal measure TM, then all the libraries rates are consistent. So then we can evaluate the payoff, and that's basically the essence of the library market model. Of course, the biggest problem here is that if we look at this this construction here, so the problem associated with the terminal measure is that this first library, so for example here, that we have this library which will mature at time t1, which is actually the closest to today, so there is the least uncertainty associated with this library. Actually, this becomes highly stochastic and very much involved process. So this is kind of counterintuitive to some degree, because the process, the library which is the closest to today, we would expect to have most certainty, the least volatility. However, if we look at this construction, there we need to involve all the libraries from our process, from our model, to bring the distant measure. So that's kind of counterintuitive, and also this is not a desired feature, that the processes, the shortest processes, the closest to today, they are the most, let's say to some degree, most stochastic, because they will involve all of the processes which are later, after this point, T1. So that's the big limitation. And then, so this is the problem with the terminal measure. This is why we often in the Libor market model, we can actually say it's a consensus these days that to work under the spot measure, unless you have really specified payoff that has to be in the terminal measure, but hardly ever happens. You can always switch between different measures. So if you don't have any preferences regarding the measures, then you should choose this spot measure. But of course, now I have to define and have to show you what actually spot measure is and how to derive it for the Libor market model. The biggest problem with the Libor market model is that the dynamics is defined on some specified tenor grid. So we have those points T0, we have point T1 and T2 and so on, but we don't have continuity in terms of times in between. So we have this grid of Libor rates that are fixed, but we cannot specify anything in between in terms of the existing market instruments. So that's basically the biggest limitation of it's also the problem with the Libor market model, as it does not provide a continuous time dynamics for any bond in a tenor structure. So the tenor structure actually is defined by those maturities of corresponding bonds. So we have T1, T2, and so on. So this will be first Libor, we have a second Libor, and this grid is fixed. So if we have a bond, zero coupon bond P, T, let me write nicer. If we have this bond P, T, T, I, we don't have, this parameter is basically fixed. We cannot have a half or we cannot do things in between. You have to then introduce some kind of methodology for interpolating those zero coupon bonds. And of course, that because of this kind of structure, we cannot really nicely fit this framework to a money savings account that we have seen, for example, in the case of the short rate models, where we have this numeraire associated with the money savings account, and then we have this continuity that we can discount from any point in time. So, for example, if we have a payment happening at this point, we can always bring it back with the numeraire. Of course, in this structure, this is not the case because we have this discrete grid, and this grid determines the processes. So that's a little bit more complicated. So if your payment will be in between, then you have to do something extra. The use of a continuous account as numeraire in the Libor market model does not fit very well to this discrete setup that we have in the Libor market model. So that's kind of something that we have to think of. If we talk about spot measure, and spot measure is associated with the money savings account, the question is how to define such a continuum of the money savings account under this framework. So if we consider a tenor structure, so those taus, this is capital tau, and tenor structure are those T0, T1, T2, and so on, and we have Libor rates defined on those points, so defined on this tenor structure grid, and numeraire for the Libor model should preferably be based on a pre-assigned maturity on the tenor structure. So we have to think of the spot of a numeraire that we can associate at any point in time, even in between those grid points. We have to associate this numeraire with corresponding zero coupon bond. So we have to somehow link the point in between here to the point, to the instrument which is defined on the grid. So this is kind of assignment that we have to do right now. And that would be used as definition for the spot measure for the Libor market model. So the strategy first is that let's take a look at the discretely rebalanced money savings account. So and this will be discretely because we have this tenor structure of T0, T1, T, and so on. So the strategy is as follows. We will first observe how we can accumulate, how the investment of €1 today, how this amount will be accumulated given the existing tenor structure of zero coupon bonds. So we have one unit of currency, then we can buy 1 over P0T1. So of course we know that this P0T1, it is amount which is smaller than 1. So this means if we invest 1 unit, then it's a 1 over that amount, and that will be number of units that we can buy of T1 bonds. You can think about it that this is the amount of zero coupon bonds that we can buy for €1 or for 1 unit of currency. Okay, so this is what we do for so the first part. So we have, you see now it's like the strategy is defined on not T0. We start with T1. We have T2. So we buy at time T1 the bond of this amount. Then what we do our next step, we at time T1 we will receive this amount, So this is amount that you will get at the maturity. Of course, we invested one unit. So this will be larger than 1. That will be received at time t1. Then this amount we reinvest for the second bond, T2, but this will be happening in the future at time T1. So then we have this strategy. This is the amount of money that you receive at time. This will be the amount reinvested in this T2. So of course, now this is already fixed because this is amount we received. Of course, we do the strategy again that we reinvest this money into next bond at this point T2. And then we can continue. So the whole reinvesting strategy is about investing in a zero coupon bond, taking all this amount and then reinvesting in a new one. And this is essentially how this process of compounding in a discrete tenor structure would take place. And this is what we'll obtain. So if we have 2 points t0 and time ta plus 1, by compounding, so you see it's a product of all those zero coupon bonds, this is the amount that we will receive at some specified time ti plus 1 if we start from time t0. So this is, so actually here indeed, so this is time t0. So this is the full amount that you receive at time tk. It's actually, sorry, ti plus 1 if we start reinvesting from today on this discrete grid. Of course, this is the first step. We still have to link, okay, so this is nice because we can kind of define the structure on this discrete grid, but still this doesn't answer the question how to define amount if we are in a point in between. So what we can do, we can define it slightly different. So we have this compounding until time ta plus 1. And if we are here, if we are at this point and we would like to see how much money we have gained, not until this point, but into point in between, what we can do, we can multiply this amount. We can multiply with zero coupon bond. This is, let's say, this is point here. This would be our time t, if we are at this point. So this would be amount that we have to multiply with pt, ti plus 1. This means that we are rolling. We are exceeding after the time t. And then what we do, we discount this amount until this point, and discounting would take place with pt, ti plus 1. So this is basically the construction how we can define amount accumulated using the discrete tenor structure until the time in the grid. So you see now we kind of define it to be continuous because now we can say at every point time t, if it's t, we compound 2 times and then we discount from the last point, grid point, to today. And this means we can actually define it to be a continuous structure for this discounting process. And this is our definition of a spot Libor measure. So spot Libor measure will be associated with this quantity. And then we have here a little bit notation is slightly different. So now we have to make it sure that if t, how to link t to the next bond. And this would be defined here. So if we look here, mt is defined as minimum I, such that ti is the bigger than t. So it's always this expression here tells you that if we are at any point here, we always take the first point on the grid of tenors next to t. So first one after t, that would be our MT index. And this is nicely defined in this way. So here we have kind of, if we analyze it further, we see that stochasticity here, those periods here, those are not stochastic quantities. You see, it's a tk minus 1 tk, but this does not depend on time t. Only this part depends on time t. So this is kind of interesting way of expressing money savings account. But this allows us to define this spot Libor measure because now this MT will be our numerier. We would like to define the measure of the Libor. So we would like to switch from a TI measure. We would like to switch it to this TM measure. So this means that if we are here, or we have payment at this point, we have this kind of running we have a running numerier with us. So we don't need to anymore to switch everything, all these dynamics of the processes until the terminal point. We can actually have running measure, numerier measure, MT. And this is also very nice because this also nicely corresponds to the strategy to the approach we had for the short rates, where our money savings account was a numerier. So we had numerier MT, and now we will have exactly the same. However, now our MT will be much more advanced, because in the past we could do, if we had to process DMT, we were always just having RT, MT, dt. So if we want to discount something from any point, we had to just integrate or discretize this MT. We had to just integrate over RT. So then MT is defined as T is 0 and then E, and then we have a T0 to T. And here we have let's say RS ds. So if you like to discount something from time t to today, or this would be, for example, maturity time t, then we always have to use this numeraire for discounting. Of course, in this case, in the Libor market model case, it's a little bit more advanced, because first we have to accumulate. There's a product of all the zero coupon bonds until point tk. Of course, this will be the next point on the grid after small time t. And then we have to use the discounting with from that moment until the time t, which is not on the grid. So this is the way how this numeraire will be defined. So if you define Libor market model, you always have to make sure that you have this also properly implemented, because this is your discounting function that you're going to use for discounting any cash flows using Libor market model. So this is very important. Of course, next step is that let's take a look how the dynamics or how the measure change will look like if we switch from MT measure, let's say, to MT plus 1. And here actually I'm defining MT plus 1, defining as N bar T. So we have two measures. We have MT corresponding to, of course, this is our numeraire, and then we have MT plus 1. So instead of just doing this directly, defining the generic setting, we would like to see how the measure transformation will look like if you would like to switch from MT to measure MT plus 1. So to the next iteration, or we have this point and we add one more, let's say we are moving by one in our grid. And this is the procedure what we do. We again apply the Radom's-Nikodym derivative. So if we switch actually here, it doesn't matter. So it's N bar T to our spot measure. So we say, okay, we have a measure defined under the MT plus 1, and we would like to switch the measure to process MT. That will be associated with this point here. So actually the measure transformation goes in this way. And then, of course, we just follow the strategy. So this will be MT at time t divided by MT0. And then with the opposite, so we see now it's MT, PT0, and then we have a PT. And of course, now again, we have to find the dynamics for, so what we have to do, we have to find the dynamics for lambda. And then we have this function psi here. And then we have lambda dw. And this psi will determine the measure transformation, the link between Brownian motions under T n. Actually, this will be n bar and m. This is the relation. And this is what we are doing here. So after substituting the definition for our money savings account, for our spot Libor, and if we just now apply the here, so this is just a substitution of what we have derived for the Libors. And if we apply the ethos to get this dynamics, we end up with expression for the measure transformation. Details for those, because there are a few steps that you have to do to really see those steps. Those are defined well in the book. But overall, if you put things together, you will see that measure transformation looks very much unlike what we have seen between if we would like to change from measure Ti to measure Ti plus 1 or Ti to Ti minus 1. So it's minus 1. So you see, it's exactly the same type of correction term we have to define. So it's very much, so spot measure, it's very much alike what we have already seen before in changing measures for Libor market model. And of course, now it is our new measure. It's not terminal measure or TI measure. It is associated only with the spot Libor, and that is defined, or the numeraire is defined as this relation of the compounding of zero coupon bonds until the next point on after time t, next point on the grid, and then discounted with the zero coupon bond. So you see, it's very much like almost the same representation as we have seen before for the Libor changes from between Ti and Ti plus 1 or Ti and Ti minus 1. And this is the final representation of the Libor market model. So if we just look here, so the dynamics for the Libor under the spot measure, and this numerier here in this case is defined in this formula. So this is our, let's say, money savings account defined under the Libor market model. So this is that here. Then we have this volatility coefficient. Of course, this one we can specify to be Lognormal, for example. Then we have to also switch this part. And this is the drift correction that has to be included in the dynamics for this Libor if we look at the Libor dynamics under the spot measure. And of course, nicely corresponds that if we have a first Libor, and we look at if you look at the summation, if we look at the first Libor, so here if we have T0, we have T0, T1, this Libor, if we are here, this Libor under the spot measure, if we look here, this will be still driftless because then the summation will not have any more terms. So everything nicely collapses. We don't have any more this problem that under the terminal measure, the first Libor will include all the Libors in the whole grid. If we look at the spot measure, it's always the next grid point that we are looking at. And under that measure, nicely, the Libors, corresponding Libors that measures are martingales. So this is extremely beneficial, and that actually is also intuitive. We don't have anymore the problem that Libor, which was the closest to today, has the most sophisticated, most complex, the dynamics structure and the drift, which involves the Libors which happen in the whole simulation scheme. So this is basically, this is it. This is the dynamics of the Libor market model. So this is the famous Brace-Gontaric-Musiela BGM model or LMM, so Libor market model. And this is actually the process, although it's not so simple to implement because you see the drift involves many Libors. So if you have 20, 30 Libors in your grid, this means you have 30 elements in your summation. So it's highly dimensional. It's a high dimensional problem. However, this is the tag. This is the problem solver if we have advanced, complicated, exotic products in the interest rate world. Of course, now we would like to, in the next part of this lecture, we will be discussing extensions of this Libor market model. So the standard Lognormal case, because here we have a Lognormal case. Then we will talk about extensions to include also volatility smile. And that can be done by inclusion of stochastic volatility. However, because of this structure, you see this very complicated drift here, then we have to really look very carefully how we choose the stochastic volatility process, because if we choose, let's say, not incorrectly, but if we choose naively to say directly Heston model and everything is nicely correlated, then I will show you that the complexity of the model significantly increases. But if we make some smart choices regarding stochastic volatility and also the dynamics for the Libors, then we can actually have both smile, skew, and at the same time, we can keep the dynamics of the Libor market model as simplified as it is possible. And here, if we talk about a Lognormal case, note that Lognormality, of course, here this is not Lognormal in general case because this summation involves multiple processes from different Libors. Once we talk about Libor market model, which is Lognormal, then we only talk about the Lognormality under this TI measure. So keep that in mind. Lognormal means only under the martingale measure what is the dynamics of the process. Otherwise, obviously, it is not Lognormal. It is a summation of different Lognormals, so that definitely won't be Lognormal.